Wave-particle duality presents us with a totally counterintuitive picture of the universe. It makes no sense to us. In all our experience, waves are waves and particles are particles, and you just can't combine the two. But the evidence says we have to. So how can we understand this? Well, let me give you an analogy for how two seemingly different and incompatible objects can actually turn out from a different perspective to be the same object. So imagine that stuck at home during quarantine and missing my teaching so much, I'm incredibly bored, and one day in deep frustration, I grab a knife and I cut a hole in the wall. And that hole is a perfect circle. Now I suddenly realize, wow, I actually have an object that will fit perfectly through this hole. And by fitting perfectly, I mean that as I slide it through, it will just brush up against the entire side of that, the entire edge of that hole. So here's the question. What shape will my object have to be in order to fit through that circular hole? That's not a really tough question. Obviously, to fit through a circular hole, the object will have to be a circle. And it fits through perfectly, and I put it through, and I'm greatly amazed. And I have so much fun with this that I pick up the knife again, and I cut another hole in the wall. My wife is starting to panic here, but it's all in the name of science, so it's all good. This time I cut a triangular hole. And I have an object that fits perfectly through this hole. Now, what shape will fit perfectly through a triangular hole? Obviously, a triangle. So I put my object perfectly through this hole. Now, the really interesting part here is that I know, you don't know yet, but I know that in fact the circular object that I fit through the first hole is the same object that I fit through the triangular hole, and it didn't change its shape. How can that possibly be? Well, so far, we're thinking, wait, a triangle cannot be a circle. A triangle is a triangle, a circle is a circle. If you're thinking in two dimensions, can you think of a way that you can have an object that is both a circle and a triangle at the same time? Well, if you think in three dimensions, you can come up with the idea of a cone. A cone is in fact an object that, looked at from one perspective, is a triangle, and looked at from another perspective is a circle. Okay, kind of cool. So you can grasp that. You can picture a cone. You're familiar with a cone. We live in a three-dimensional, possibly four-dimensional universe. But imagine trying to explain the idea of a cone to a resident of Flatland. Flatland is a book that was written in the 1880s by a mathematician, Edwin Abbott, and it is an imaginary tale of the inhabitants of Flatland. What is Flatland? It is a universe that is perfectly flat, meaning it is two-dimensional. It has length and it has width, but it has absolutely no height at all. So no resident of Flatland has any experience of height, any experience of three-dimensional objects. Now, to them, a triangle, a cone would be incomprehensible. They could never envision having an object that you could just turn and it would go from being a circle to a triangle without actually changing its shape. Could they ever work with cones? Well, yes, they could. They couldn't ever picture them in their internal subjective universe, but they would have a tool that would allow them to actually talk about cones, and that would be mathematics. Because even if they don't understand what this third dimension of height is, if they studied enough, they could figure out that it does exist, even though they cannot see it. They could work mathematically with it, but it would be beyond their ability to envision. This is the power of mathematics. It actually allows us to describe, to discuss, to understand things that our minds cannot grasp because they are completely outside of our experience in our three-dimensional middle of the universe state. So mathematics does that, and the same thing is true of quantum theory. A physicist in the 1920s named Erwin Schrödinger actually came up with a mathematical equation to relate for anything in the universe, both its particle properties, so we have mass over here, and we have shape, and we have time, and its particle properties, its wavelength. And notice that in there is Planck's constant. This is actually the reduced Planck's constant. It's a slightly different version of it. We call this h bar, but this is based on Planck's constant. So you put in Planck's constant, and using the Schrödinger wave equation, you can fully describe a particle, a subatomic particle like an electron, using both its wave and its particle properties, in the same way that the inhabitants of Flatland could put the equations of a triangle together with the equations of a circle to figure out the mathematics of a three-dimensional cone.